Okay, welcome back everyone. This is going to be a video lesson for pre-calculus about the natural exponential function. So by now you should have already watched the previous video about exponential functions, and hopefully you've tried some practice problems and worked on some homework, and hopefully you feel good about that section, because this section is really just going to build upon what we were talking about in that video. All right, let's go ahead and get started. The natural exponential function. So I want to remind you of something that we kind of hinted at last time, but let's explicitly say it now. And that is that different exponential functions pass through 0, 1 with different steepness. All right, so I hinted at this last time, and maybe it's not even really clear what I'm saying here. Let's draw some pictures. I think if I draw some pictures, that's going to help make this clearer. So when I say different exponential functions, remember last time we had a definition for what an exponential function is. F of x equals a to the x. So when I say different ones, I really just mean different bases. Like exponential functions of different bases is really what I'm talking about here. Generally the larger the base, the steeper the curve. So for example, I'm going to try to draw two little sketches here of two different exponential functions. These don't have to be perfect pictures, but it's just going to illustrate the point. We know that they pass through the same y-intercept. If they are truly just a to the x, then they are going to pass through 0, 1. We also know they're going to have this asymptote here, and we know some things like their domain and range, but we don't even need to talk about that right now. All right, so the first one that I draw, I'm going to try to draw something like y equals 2 to the x. It's going to look something like that. You know, maybe not exactly, but close enough. And for the next one, I want to try to draw y equals 4 to the x. So this is what I mean about how they both pass through that same point, but the 4 to the x one, it does so much steeper. If you imagine this as like a roller coaster that you were riding up from left to right, you know, this one's more of a gentle slope. You're going up and up and up. Okay, fine. But the 4 to the x one is super sharp, like you're going up at a very steep rate. That's what I mean by the word steepness. Or in other words, if you were to try to climb up this, you know, this looks like a hill that you could get up, you know, walk up this hill, climb up the part that gets kind of steep. But this one looks almost like a cliff. This looks like this would be really hard to climb. It almost feels like I'm talking about slope. Isn't slope kind of the way that we measure how steep something is when we're going from left to right? You know, a gentle slope or like a really steep slope. And generally, we only talk about that for straight lines. And what we're dealing with now is not a straight line. What we're dealing with now is definitely a curved line. But it almost feels like we're talking about slope. It turns out that there is one base called E such that the slope, I'm going to put this in quotation marks, the slope of y equals e to the x at that point 0, 1 is exactly 1. I'm going to draw a picture of this. And then maybe we'll be able to compare it to the two pictures above. So above, I drew 2 to the x and 4 to the x. This is just going to be another exponential function. This is just another base. It also passes through 0, 1. But in particular, this one passes through with a slope of 1. So what I mean is, at that little part of the curve, it kind of looks like a slope of 1. And then the rest of the thing is the general shape that we expect. Like that. Looks pretty similar to the 2 to the x example. And in fact, e is just a little bit bigger than 2. So this is a graph of y equals e to the x, and the number e is approximately 2.7. It's actually approximately 2.71828. I'm going to put a box around that. This is also known as Euler's number. Okay, so this mathematician, that name is pronounced Euler. Sometimes called Euler's number or Euler's constant. So, what's so special about this? Well, the answer to that is going to be kind of gradually revealed to you over this course, and if you take calculus, and if you take calculus 2, and if you see it in some science courses, there's a lot of special things about this number. But what I'm showing you now is one way in which it is unique. So when I talk about the slope of this curved line at this point, what I really mean is if you were to draw a straight line at that part of the curve, following the same kind of steepness as the curve, this would have a slope of 1. And what I tried to do in the two pictures above is I tried to draw it so that you might see this one has a slope that is less than 1. This one has a slope that is greater than 1. But a slope of 1 is kind of like would make a 45-degree angle with the x-axis. So the function f of x equals e to the x, the exponential function with this particular base, is called the natural exponential function. So it certainly sounds important because it gets its own section dedicated to it, where this whole video is about the natural exponential function. I can't tell you all the interesting things about e in this video. It's going to be kind of spread out over multiple videos and show up in calculus. But it suffice to say that e is sort of one of these really interesting constants in math, kind of like the number pi. So e is an irrational number, just like pi. In fact, both e and pi are examples of what are called transcendental numbers. And this means that they have an infinitely long decimal representation with no repeating pattern and no end. So it starts off 71828, but then it just kind of goes in what seems like a random direction, and it goes on forever. That's actually been proved. It's been proved that the decimal never ends and never gets into a repeating pattern, which is kind of interesting if you think about it. Like, how would somebody prove that? How do you prove that something doesn't happen? And then there's other interesting properties, like it's been proved that this is not the root of any polynomial. I don't know if anyone else finds that interesting, but I find that kind of interesting. All right, so there's also what we discussed up here is kind of a way that you could define this number e. I'm defining it to be the one base that has this property. In particular, it makes the slope 1 at that spot where you pass through the y-intercept. There's also another way that we could define e that I want to tell you about. Another way to define e. This is going to be a sentence instead of a picture. It is the value that this expression approaches as m becomes infinitely large. Period. So take a look at that sentence for a minute. It's kind of a weird sentence, isn't it? This is a weird looking expression. We're saying you let m become infinitely large. So we don't really just plug in infinity. Like, you can't just plug in infinity like it's a number. Infinity is something that you can approach. So you could imagine m being a very large number, like a million or a billion or a trillion. What would this expression become? The closer m gets to infinity, the closer this expression gets to 2.71828. That's kind of weird, and that's kind of surprising. Here, I'll tell you what. Let's see if we can kind of demonstrate this. I've got a calculator. Let's look at, all right, parentheses, 1 plus 1 over... Like I said, you can't just plug in infinity. But I'm going to put in a large number here. Let's do like 999,999. All right. Close the parentheses, and then I'm going to raise this to the power of that same thing, 999,999. So did you see what I got in there? This, but I used m is 999,999. Evaluate this. 2.71828 something, something, something. So it's interesting that this expression would equal anything at all. Why is it around 2.7? It's an incredibly large exponent. But the thing that's in parentheses is incredibly close to 1. And we saw something happen like that last time when we were talking about interest, that you could have something in parentheses that's approximately 1. You could raise it to a large exponent and still get like a medium-sized answer. So that's kind of what's happening here. Anyway, here what we've talked about is 2 different ways to define the number e. These 2 different ways seem completely unrelated to each other. One of them is based on this idea of slope at the y-intercept, and one of them is based on this weird expression here. Now, I want to tell you that technically, both of these definitions for e should use calculus to justify them. However, here in pre-calculus, we can still understand that there is this special number, e, with these properties, and that it's approximately 2.7. In this class, I would like you to know that pi is approximately 3.1 and e is approximately 2.7. You don't have to know, you don't have to like know all the digits, but knowing that it's around 2.7 would be good. Let's start to see how the number e shows up in applications. I think I mentioned at the end of the last video, I think I mentioned that we were going to revisit interest. So let's do that. So last time we said A of t equals P1 plus R over N to the NT. This is a formula for computing compound interest. And we said, you know, P is the principal, R is the interest rate, N is, let's say what N is. N is the number of times per year that interest is compounded. And I said that compounded is like another word for applied. How often is the interest applied? And, you know, sometimes N is something like 1 if the interest gets added on once per year. Sometimes N is something like 12 if the interest is applied monthly. And I had a note last time where I said a key idea is when interest is compounded more often, it results in more money. So that would mean when N is larger, the amount will be larger. So maybe you want to compound the interest every month, or maybe even every week or every day, and you'd get a larger amount of money. This is assuming like the principal and the interest rate are staying the same. So you could try 365. You could try, you know, compounding interest every day of the year. But you might say, well, what if we compound interest even more than that? What if you compound interest every minute of the year? Figure out how many minutes there are in a year and put it in there. Or what if you say, I want to compound interest every second of the year? Or what if you say, I want to compound interest even more often than that? Can we compound interest more often than that? So here's what we're going to do. We're going to wind up deriving a new formula for interest. And in order to derive it, we need to do a little trick here. I'm going to introduce another letter that doesn't appear in the original formula. I'm going to introduce M, and I'm going to let it equal N over R. So M doesn't appear in the original formula, but N does and R does. I could say that if M is N over R, then the reciprocal of M is R over N. And if I did a little cross multiplication, I could say N is MR. So I introduced this new quantity M, and I'm writing it in a few different ways. I'm saying M is related to R and N in these ways. Let's take that formula for interest that we wrote above, and for now, I'm just going to write it again. We're going to be able to derive a new formula from this. Let's just write it for now. NT. I'm going to circle some things. I'm going to circle R over N. And I'm going to circle the N that's up here. And what I'm planning to do in the next step is the R over N that I circled is going to get replaced with this, 1 over M, because R over N is equal to 1 over M. And the N that I circled up here is going to get replaced with MR, because we said that that's equal, N is equal to MR. So what do we have here then? P1 plus 1 over M raised to the MRT, Mr. T. You could say this is a new formula for interest. It's not really like any nicer. It's not any easier to use. We're going to do a little bit more with it. There was a property of exponents that said when you have multiple things up here in the exponent, like M times R times T, we could actually rewrite this as P, and in parentheses, what I'm going to do is raise this to the M and then raise it to the RT. I added an extra set of parentheses there, or brackets. We're allowed to do that because of properties of exponents. You could raise it to the M and then raise it to the RT on the outside. Now the question is, a minute ago we were talking about what happens when you compound the interest very often, like the number of times per year that interest is compounded. That's the number n. What happens as n gets very large? I'm going to say as n approaches infinity. That's the idea of n getting very, very large. I'm going to say as that happens, so does m. As n gets very large, so does m. How do I know that? Because we defined m to be n over r. And we're assuming in this discussion that the interest rate is staying the same. Interest rate is r, it's just some constant. So if n gets really, really large, m gets really, really large. Well, when that happens, this expression becomes e. It appears in this work that we were doing above, and we're saying that if you compound interest as often as possible, you try to compound interest infinity times per year, this thing is just going to become e. And we have a name for this. We say that this is continuously compounded interest. I'm going to underline that. You know, in the previous section, we talked about compound interest. This is a sort of variation on that. Continuously compounded interest is calculated by. It has a formula which we just derived above, and it is A of t equals P e to the RT. It's what we wrote above, but we let that expression become e. And since we're establishing this as a formula, I'll just write what these things all mean. A of t is the amount after t years. Capital P is still the principal, which is another name for the starting amount. You know, you have some kind of interest is being applied to something. It's like an investment or a loan or something else. R is still the interest rate per year. You know, T is the number of years. And the idea behind this is that interest is being compounded I'm going to put this in quotation marks, every instant. The number of times compounded per year approaches infinity. Does it ever quite get there? Does it ever quite get to infinity? Well, this is a topic that kind of gets discussed in calculus, but I'll tell you that the overall way that we want to think about this is it's kind of like an asymptote. You know when something approaches an asymptote, but it never quite gets there? It gets incredibly close. That's kind of what we're talking about here. We can get larger and larger, but we don't really ever just plug in infinity like it's a number. It's more like it's a concept that we can approach. So every instant I put in quotation marks, or every moment of the year, we're just, compound interest, compound interest, compound interest. And it's actually a simpler interest formula, isn't it? Because, here's the old one. Now we can see both of them side by side. So which one do we use? Like, which formula? Do we get to choose which one? Well, the answer is it depends on the problem. If a problem says that interest is compounded once per year, or quarterly, or monthly, or something like that, then you have to use the original compound interest formula so that you can put in the correct thing for n. But if a problem uses the word continuously, if a problem says here's, some principal and the interest is compounded continuously, then you know that you use the second formula, which is actually simpler. Still have the principal and the interest rate. E is just a constant. E is around 2.7. Most calculators will have a button for E. I should probably mention that if you were using this formula, you probably should not just say 2.7. That would probably be rounding it off a little bit too much, a little bit too soon. I'll show you. My calculator has a button for E. I don't know if you can see it, but it actually has a button for E raised to a power. If I really just wanted to say E, I could say E to the 1, and there it is, 2.7. It looks like it has a pattern, 1828, 1828. Would you believe that it actually does not have a pattern? It changes after this to some other digits. Kind of interesting. All right, but my point is, it's better to use the E button on a calculator instead of just 2.7. Let's do one problem. Let's say we're given... I actually want to tie this in with a problem that we did in the previous video. So I'm going to use a principal of 100, an interest rate of 0. Well, this is going to be 10%, right? And I'm going to ask, what is A of 3 if interest is compounded? We're going to have 3 little parts to this. Annually, monthly, or continuously. And I'll do this problem for us. The truth is, we've already done 2/3 of it in the previous video. But I thought it would be nice to see these results side by side. For part A, annually, we should be using the first interest formula. So 100 times 1 plus 0.1 over 1 raised to the 1 times 3. I could kind of do part of this by hand. I could say 100 times 1.01 to the 3. That's as far as I could go by hand. Then I would use a calculator to finish this. And for part A, I get 133.10. And that is a number that we saw last time. Part B says same principal, same interest rate, but now interest is compounded monthly. So this time A of 3 is going to be 100 times 1 plus 0.1 over 12 raised to the 12 times 3. If we try to work this out, it's 100 times 1.0083 repeating to the 36. And last time I told you that when I did this, I got 134.82. That's rounded off to the nearest cent. So we're not going to use calculators a whole lot in this course. Interest is just one of the topics where we kind of need to. I want to warn you that in these problems, you see this 1.0083 repeating. You don't want to round that off too much. Like, really, it's better if you don't round that off at all. Because when you round it off and then you raise it to the 36, that could change the answer more than you expect. So try to leave, that number as is. Don't round anything until you get to the final answer. All right, and then the last one says continuously, so now we get to use our new formula. Now we use P e to the RT, so P e to the RT. This is going to be 100 e to the 0.1 times 3. And I put this into a calculator. I used the E button on my calculator, and I got 134.99. Okay, so we get to see these three answers side by side. What's the big deal here? I said that when you compound interest more often, it should result in more money. Okay, so this is a little bit more money, right? 134.99 instead of 134.82. It's not a very big difference, but it's a little bit. And we're only starting with $100 here. $100 is a very small example. We only waited 3 years, so we didn't wait a very long time. If this was like a larger investment over a larger period of time, then the difference between these might become a little bit more noticeable. I want to mention, I think I said something about this last time, but generally, like if you're taking out a loan, like a student loan or, bank loan or whatever, house loan, generally you often you don't get a choice over how often the interest is going to be compounded. Compounding continuously is pretty popular. A lot of banks use that. Sometimes things are compounded daily. It's kind of interesting when things are compounded daily, it kind of raises a question of what should you do about leap years? And the answer to that is it depends on the bank. Different banks have different rules for how to deal with a leap year. Some of them just don't apply interest on the leap day. Some of them use 365.25 as the value of n. So there's like different rules depending on whatever the bank says, usually in some kind of fine print. If it's compounded daily, that is. But if you're taking out a loan or, starting an investment, usually the things that you have the biggest control over are the other things like the principal, that's, the starting amount, the interest rate, you might be able to negotiate that. You might be able to, or you might not. And then the amount of years that it's going to be. All right, so if you have an interest problem, just remember, both formulas are important. It depends on how often interest is being compounded. All right, so this has been kind of a shorter section so far, and we're going to be finishing up soon in just a minute. But I can't help it. I actually want to show you a few cool things about the number e. So bear with me for just a minute while we do this. So since this is pre-calculus, we like to sometimes give you a little preview of things that you might talk about in calculus. So I want to talk about a few facts about e from calculus. Earlier, I was saying that e is the special number. And I'm just going to tell you 4 quick facts about this interesting number. This first one is that e is actually equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus dot, dot, dot. This keeps going forever. Side note, do you remember what factorial means? We don't use factorials very often in this class, but like 4 factorial means 4 times 3 times 2 times 1, etc. So when you see a exclamation point, that's a factorial. You're multiplying that times all the previous integers. So anyway, look at this weird formula for e. Is there any reason why this looks like this should add up to 2.7 something? I find this really interesting. It's interesting to me that this adds up to anything at all, because this is like a sum that's infinitely long. And everything that you have here is positive. Positive 1 plus a positive quantity plus a positive quantity plus something positive plus something positive. You keep adding positive stuff forever. You might think that the right-hand side is just going to keep going up and up and up and become some incredibly large number. It actually equals e exactly. That's something that you could prove using calculus. But for now, I just thought I would tell you. Technically, you would need calculus 2 in order to prove that. Another interesting fact about e is if you were to look at the graph, this is going to be a very rough sketch. If you were to look at the graph of y equals 1 over x, and you were to look at the region between 1 and e, and I'm going to shade this region in. So what's the fact? So what's the fact that we're getting at here? It's that if you set this up in this particular way, that the area of this shaded region will be exactly 1 square unit. Which, I don't know, kind of interesting, kind of surprising maybe. Another interesting fact about E from calculus, there is a problem known as Steiner's problem. And it says, for what positive number x is the xth root, that's kind of hard to say, the xth root of x the greatest? All right, so you can imagine doing like the cube root of 3, you know, or the 4th root of 4, or the 5th root of 5, or the 10th root of 10. The 9th root of 9. What number is going to get you the greatest result? The answer is e. The eth root of e is actually the greatest result. Interesting little problem. So I may have mentioned earlier that e sometimes shows up in some surprising places. That's kind of surprising to me that answer is e. And one more interesting fact about e from calculus, and this is called Euler's identity. Euler's identity is a formula, and it says e raised to the I pi plus 1 equals 0. And off to the side, I should say what I is. In this context, I is understood to mean the square root of -1, the imaginary unit. So what can I say about Euler's identity? Well, in pre-calculus, we mostly just stick to the real numbers. We don't use imaginary numbers that often, but when we do, sometimes we use I to represent the square root of -1. Euler's identity is really interesting because math geeks like me really like this stuff because it's a really kind of elegant formula. It's sort of said that this formula includes the 5 most important numbers in all of mathematics altogether. It has e, I, pi, 1, and 0. They are the 5 most important numbers. It also includes the most important operations. It has addition. It has multiplication, I times pi. It has exponentiation. And it also has an equal sign. So it has the most important symbols all appearing in one formula. And believe it or not, Euler's identity does have some applications. It seems like some weird abstract thing, but this is pre-calculus, so we're getting a little ahead of ourselves. I'm giving you a preview of some stuff that shows up in calculus. In particular, I like to prove Euler's identity at the end of Calculus 2. And some of you might plan to take Calculus 1 and 2, and some of you might not. But that's okay that we spent a couple of minutes on this. This has applications to engineering and other stuff. Science and engineering is usually what I think of when I think of applications of this. All right. All right, so thank you for bearing with me for a couple of minutes while I showed you some geeky things about the number e. I think e is a really interesting number. Maybe at some point during the course I'll show you some cool things about the number pi. Anyway, that's going to be the end of the section for us about the natural exponential function. The next 2 sections that we talk about are going to be about logarithms. And you may have seen them before in an algebra class, but you know, it's good to get a review of them, and we might do some different things with them that you haven't seen. So stay tuned for that. And I guess until then, take care, and I'll see you soon.